Okay, apparently we are live now. So welcome everybody for this coffee break today. I have my tea. I don't drink coffee, so I hope there's some tea drinkers as well. That I'm not alone. Um, about my person, I'm a Sergio Grond. I'm an application specialist here at Eddyfi. I work in the application surface team. That's why I have a surface probe with me at the moment that you will get to see in action a bit later. And today I will be talking about far-side inspection and how we manage the lift-off problems. Just in general, if you have questions, feel free to leave them in the comments, and either I will answer them right away if I see them, or we will come back to them in the end of this presentation. Let me put this on full screen. Looks like this. So as I said, I'll be talking about far-side inspection and lift-off management. Just for the agenda, I will start with the lift-off management, then go to far-side inspection. In the end, I will take a scan on an aluminum plate to detect some far-side flat bottom holes. And I will work with the Magnify software that we have here at Eddyfi. For the lift-off management, we usually look at the impedance plane, but the impedance plane itself can always be different. So the operating point can vary depending on which material we're working with. So for example, here with aluminium, the operating point is at a certain point on the curve. And then if you move the probe, let's say you balanced on aluminium, then you move the probe in air, you get a certain lift-off signal here illustrated in red dashed lines. And let's say on carbon steel, you will be somewhere else on the impedance plane. So your operating point is somewhere different. Hence, the lift-off signal will look differently as well compared to your defect signals. So this is always to respect when you need to know on which material you're working on, and you preferably balance on this material and then make a lift-off, and then you see the operating point changing. And when you have all this information, the best way to improve the signals is if you take this view. So we switched from the aluminium lift-off point, and we only take this portion of the impedance plane, and we balanced on aluminium. So where you see the 0, 0 was directly on the material, and then we rotate the whole signal in the Magnify software so that the lift-off will be horizontal. So when the lift-off is horizontal, then we will only look at the vertical change in the signal. So as you see now, if we have a lift-off change, the signal would move from operation point a bit towards the left, but the defects will always go kind of vertical. So by only looking at the vertical change, we kind of cancel this lift-off change, because that's not what we want to be sensitive to. So we choose to rotate the signal in this direction, and then we won't see the lift-off affecting the signals that much when we have a good phase separation. And afterwards, to improve this signal that we captured, we apply some horizontal gain only in the y-axis. So it won't, you see the difference, the lift-off gets boosted a little bit, but the defects get boosted much more. So you will see the defects even clearer. So that's the main principle how we manage lift-off. There are other ways, but this is more hardware kind of. We can choose different coil sizes. So here's illustrated on the top right side. There is the black coil is a 2 millimeter coil. The green one is 3.5, and the orange one is 5 millimeter. It's just an illustration, so don't take all the values here for granted and set in stone, but just to give you an idea. And in the graph, you see the normalized defect signal. So 1 is 100% of the signal. So So the coil is touching, the probe is touching directly the material, and below you see the liftoff amount. So let's, for this 2 millimeter coil, the black coil, and we lift this one up in the air, so we perform a liftoff. You see, let's say after 1.5 millimeter of liftoff, we already lose almost all of our signal. But on the other hand, if we take a bigger coil, 3.5 or even a 5 millimeter coil, they can tolerate a bigger amount of liftoff. So the signal is obviously maximized when you are directly in contact with the surface, but this cannot always be the case. Maybe if you have a paint layer, or there's just a certain, maybe a rubber layer of a certain thickness. So if this is like 1 to 2 millimeters, then if you know this thickness, then you can choose, or we can choose the coil size accordingly that we put inside the probes. So meaning now for the 2 millimeter coil size, after only 1 millimeter of liftoff, we're already down to like 25% of the maximum signal strength that we could have if we were directly in contact with the material. On the other side, for the green coil, 3.5 millimeter, after 1 millimeter of liftoff, we still have over half of our signal strength. So if this we can also play, it depends on what type of defects we're looking for. And then also that the bigger we go in the coil size, the more liftoff we can tolerate. But we will be a bit less sensitive to really, really small indications. So there's always this sweet spot we have to find between taking super small coils, super big coils, and then being sensitive to what we want to, and maybe liftoff or not liftoff. I hope this gives an idea on how we choose the elements inside the coils, inside the probes. But in general, what happens when you have liftoff? Here's an example of the 3 cracks. One is 0.5, 1 millimeter, and 2 millimeter. They're directly on the operating point where we balanced, and we add liftoff. That's at 0 millimeter liftoff. Then we add some liftoff, and you see that all the defects get kind of smaller and travel towards the left, towards the more liftoff. So they will move along this liftoff curve. They will stay horizontal, but afterwards they will move wherever the liftoff curve is going, because you have a certain amount of liftoff and the signal goes in this direction until the defects become smaller and smaller, and we won't see them anymore, and we're just in air. So this is what happens usually, that the phase stays the same of the defects when only the liftoff changes. They will just be seen as a smaller amplitude. So all this information will be important to what I show you afterwards. So yeah, that's how we handle liftoff. It was a short recap of what we do with liftoff. Now we'll go over to far side inspection. And here is a small illustration. That's a probe that will move along a surface with a direct contact. It's always preferred to have a direct contact with the inspection surface. And a probe that looks for far side indications, it's usually used with a low frequency. So something between 100 hertz and 25 kilohertz. And also, we should have a material that is non-ferrous. Let's say if it's a ferrous material, then the eddy currents will kind of be pushed to the surface and won't be able to penetrate the material as for stainless steel or aluminium. Again, we will look at the impedance plane to see our signals. And when you move the probe over those defects, you see the first defect is bigger in volume, is deeper, closer to the surface. So we see it with a higher amplitude. And then the smaller the defects get, or the further away the defects are from the surface, they become smaller, and then they open up with the phase. So they they move towards the right side in this case. So that's how we can also differentiate how deep a defect is by looking at the phase of the defect. Yeah, that's it. Deeper defects increase the phase shift. For the far side inspection, we have a rule of thumb that we often, the first time you hear about an application, we ask, okay, how thick is the material? What material do you have to inspect, and how deep and how big are your defects or your indications? And if this rule of thumb, here's the coil illustrated, the coil OD. It's more or less the OD of the coil can be translated to the depth of penetration. That's a rule of thumb. It can vary, but it gives you a good idea of if I have a 5 millimeter coil, my depth of penetration will be roughly 5 millimeter, where I still have a good quality signal. In some cases, it can be more, but then we would need to tweak the setup accordingly, and it also depends on which material you're working with, surface condition, and several things. So just maybe keep this in mind. And if you want to penetrate 5 millimeter deep, you take a 5 millimeter OD coil in the probe coils. And you will be sensitive to indications that penetrate at least 20% of this wall thickness from the far side, and that are maybe twice the volume of the coil, or twice the diameter. So you see it here illustrated. The red part is the flaw, the defect, and it's roughly twice as long and 20% depth of penetration. Okay. Now, if you put those two this information together in one impedance plane, so you'll see we perform a liftoff usually. Then here's the liftoff is already rotated horizontally, and then we maybe scan over a small notch that is surface breaking. Then it will be a shallow or a small amplitude with a smaller phase closer to the liftoff. If we scan a bigger notch, so the illustration goes a bit too far here, it should only scan this one, we will have a nice defect shape. It could look like this. Then, yeah, large amplitude, greater phase shift towards the liftoff. And then that's the third indication that is a little bit subsurface, but still closer to the surface. But you see it will open up a bit and also be a bit smaller because it's not surface breaking. And then the last, if a larger phase shift, then the last indication, well, it's scanned this one, should still be on the material, has a even greater phase shift, but it's quite small now because it's deep inside the material. So yeah, the deeper it goes, at one point we will also lose it. So we should stay close to the surface. With a certain amount of liftoff, we will start to see less and less of the indications, but they stay with the same phase. And the further they are in the material, the further they will open up in the phase. And at one point they will also, let's say, disappear because they get too far away for the eddy currents to see them. Now I will come to the scan. I have my plate here with several flat bottom holes. Some are all the way through. There are 3 all the way through. And basically there are 4 types of holes, of 4 depth. The most shallow one is 0.79, 0.8 millimeter. This one 1.6, around 3.17, and 4.776. And the plate thickness is 6.4. So some are all the way through as well. I will not focus on those because they will be easy to see. And this one is like 75%, 50%, and 25%. And I will be using an iFlex, one of our standard iFlex probes, the extra large one, because you want to penetrate to roughly 6 millimeters. So I will have 6 millimeter coils, and I'll be working in a long single driver topology for the people who know what topologies are. And I will go quite low in frequency. So the central frequency of this probe is 5 kilohertz, but in my setup, I will go down to around 1 or 0.8 kilohertz. So let me switch to 95. We took some test scans before. So let me just show you what I have here. That's the iFlex probe with rather big coils. And I plugged a standard encoder to it. And then I want to make sure, well, now I know that let's say my defects are here and there is a long notch. So I want to balance around here where I don't have any indications. So I have to have a nice balance point. So if you know this in your application, it's preferably to balance on this surface. So let me balance. And then I'll just scan along here. I did the lift-off adjustments already in advance. So, and that's a good example for something you should not do. I moved a bit too fast, so that's why you see 2 black lines in the scan. Yeah, because we're quite low in frequency, I should move a bit slower. Those holes are all the way through, so I want to focus on this section here. And what I did as well in advance, I added a sizing curve. And my sizing curve sizes with the phase of the indication. So here, for example, for this indication, we have a 91.4 degrees. And because I calibrated the core, I built a sizing curve accordingly. It sizes me this indication as 3.1 millimeter. And if I maybe switch back real quick just to show you, 3.17. So the sizing is not perfect, but I guess it's quite accurate. And just please don't forget, with pancake eddy currents or with an iFlex probe, we do it's more an approximation. We cannot call it sizing because it always depends on how many points we have on our sizing curve. And so if you just have like 2 example points, then the curve would just be one straight line. It might be not super accurate all the time. So it's more an estimation. And then also maybe one scan to another can vary a bit, and then also where you place your cursor. So now it gives me something between, down here you see the value, 3.2 millimeters to 3.1. If I take this one, it's around 1.8, 1.7. So just to switch back, it should be around 1.6. So I guess we're not off too bad. This one, make the cursor a bit smaller. I think it has the same. Yeah, 1.7. You're also around 3.2. So here I didn't have any lift up. So now we'll add a sheet of, let's say, 1 millimeter. And I'll perform the same scan, and just keep in mind how the scan looked like, how well you see the indications, because now the indications should become a little smaller because we're a little bit further away from the surface. So balance, I scan. I try to move a little bit slower now. Don't have a black line. All right. I was not perfectly in the middle. So let's focus on those. And that's two other indications we saw already. But let's refocus on those. They were clean. So, okay, I didn't focus on the voltage value we had, but I think we have something like we had before 1.2 maybe. Now we are down at like 0.8, so we lost some amplitude of the indication, but the phase is still very similar. So we're around 91 degrees, and we're still, since the sizing curve is based on the amplitude, we still get the similar sizing of 3.2, 3.3, 3.1. If we take this one, 4.7, and I think we should be, around 4.76. And here we also lost some amplitude, but it didn't affect our sizing. So that's really, really helpful in Magnify, that you can build your sizing curve based on the phase of the indication. I think I saved the other data. So let's just say here we're around 0.8 volt. And if I go to the sizing that took before, what's this one? No, I don't want to save it. Yeah, here I took an example skin where I moved super fast. I wanted to see where the limit is. Take this. And yeah, we were around at 1.5 volt, and yeah, this one was a bit shallower. So yeah, I hope that gives you a good idea of how sizing curves can be performed in Magnify, and how we tolerate, or how much liftoff we can tolerate, and how we manage liftoff, and also that for Farsight, even though they're only like 25% deep, we can still see them. Oh, I didn't show you this one. Sizes me 0.8 millimeter, and it's actually 0.79. So that's not too bad. And yeah, there's a certain amount of liftoff, we will lose the defect and you won't be able to size it anymore, but we can tolerate up to a few millimeters of liftoff and still penetrate like 75% of the material. Oh, I didn't pay attention to the questions. It was like, good morning, everyone. Hi, Sergio. We are excited for this coffee break. Thanks. Why can only non-ferrous material be penetrated? I actually mentioned this a little bit during the presentation. The thing is with ferrous material, because it's really, the more they are magnetic, the harder it is to penetrate, and the eddy currents will really only stay on the surface. They will move along the surface, they kind of get pushed to the surface. We say this usually, we don't penetrate ferrous material, but it's not 100% true. We have some custom applications where we were able to saturate or desaturate with really strong magnets. So inside the probe, close to the surface, there were strong magnets placed who could kind of cancel this ferromagnetic effect. And afterwards, with the help of those magnets, we were able to see subsurface defects in ferrous materials. So let's say if our standard probes, you don't have magnets integrated in them, but if you have an application and you're interested in seeing something subsurface ferromagnetic material, you can contact us and we will maybe try take some scans. You can maybe send us the sample and we can try something out with placing some magnets around the coils, and we were already successful by doing this. Yeah, as you saw, the scan speed affects the signals, but more also the depends on which frequency you have. The lower the frequency you have, the slower you have to go. So if you If you use a high frequency probe, you could move a bit faster. But say I was still moving, it take me half an hour to scan this plate. I was still moving, I scanned it in a few seconds. So just the moment when you see some black lines appearing when you use an encoder, you notice, oh, I went a bit too fast. I lost a few data points on my way, but still, you can still analyze the signals and just move a bit slower next time. But so yeah, it just affects the scan slightly, but you can still detect what you want to. I see you have a low frequency probe with big coils. Would this be the same with a small iFlex probe with smaller coils? Good question. Yeah, indeed, I have a low frequency with bigger coils, low frequency probe. And if you have like the small iFlex, the standard probe, it's more made to look for shallow indications close to the surface. So also if the iFlex probe, you cannot go that low in frequency. So if you want to penetrate deep in the material, a bigger probe with bigger coils is recommended. And I mean, you could still give it a try if you look really for shallow indications close to the surface. But the iFlex small probe is more made for really small indications and surface breaking. Yeah, exactly how the text in other comments. Feel free if you have other questions to just email me if you're not live now, and we will try to answer your questions. So thank you very much, and have a great day.